Hi there, my name is Yifan. Welcome to our CVPR poster. I would like to introduce to you isopoints, a hybrid representation for optimizing neural implicit surfaces. Neural implicit functions have emerged as a prominent representation form for 3D geometries. It is a continuous representation promising infinite resolution and unrestricted topology. It has many applications, including surface reconstruction from point clouds and multiview reconstruction from images. Our goal is to learn neural implicit functions to represent single shapes based on imperfect observations. Existing work struggle to accomplish this task robustly and accurately, as the network overfits to the imperfections in the data. For example, when fitting a neural surface to a noisy point cloud, droplets and bumps emerge where there are outlier points and holes. In this work, we propose to alleviate these problems by introducing a hybrid neural surface representation using the implicit and explicit representations interchangeably. On the one hand, we still have high resolution and topology flexibility thanks to the implicit representation. On the other hand, the explicit form makes it possible to incorporate a large set of tools from classic geometry processing into the training process, such as providing additional constraints in the presence of noise, as well as providing guidance to generate training samples for more efficient optimization and accurate reconstruction. The key challenge is to extract the explicit representation efficiently during the training of a neural surface. The standard way to convert from implicit to explicit is Marching cube, but is too slow for online use. In our solution, we choose points instead of mesh as the explicit representation. We call these points isopoints. The extraction contains 3 steps. They are adapted from classic point-based geometry processing methods for full GPU implementation and more robustness under imperfect implicit functions, which we have during training. On the highest level, we first obtain a sparse point cloud on the implicit surface via projection. Then we improve the distribution uniformity in the resampling step by applying a repulsion force. Finally, we upsample to obtain a dense point cloud covering the entire surface. Now, how do we utilize the isopoints during optimization? First, in multiview reconstruction, existing works generate training samples by uniformly sampling from the input image planes, which can lead to under- and oversampling certain regions. Using isopoints, we can sample more adaptively to the underlying geometry itself, which contributes to faster convergence. We can even sample based on some attributes of the local surface, such as curvature and current appearance loss, which can further boost the reconstruction quality in surface details. When reconstructing surfaces from noisy point clouds, we can use isopoints to detect outliers and formulate additional explicit regularization terms in the training objectives, which contributes to higher reconstruction quality compared to existing state-of-the-art methods that use only implicit or explicit representation exclusively. In conclusion, isopoints and implicit functions are interdependent representations for 3D geometry. Together, they leverage the implicit function's ability to represent geometry with arbitrary resolution and topology, but at the same time also improve the learning by utilizing various geometry analysis and manipulation techniques enabled by isopoints. Thank you for your attention. I look forward to discussing the details with you in our session.